So in this video, I'd like to talk about a journey that Atlassian took when they migrated for their product Trello from RabbitMQ to Kafka. Now, to set the context, Trello is a simple to-do application, kind of like a Kanban board, where you have multiple columns and you can take card from one section, move to one board to another board to another board, or rather one column to another column to another column. Now, in this one, you can very clearly see that there is a lot of thing that needs to be done in real time for a great user experience. So a lot of WebSockets are involved. Imagine if, let's say, two people have a shared Trello board, and if one person adds a to-do on another person's interface, it should be automatically added. Okay. That would be a great user experience. So this is where Trello comes in. This is what Trello does. Now with that in context, let's understand that their journey from RabbitMQ to Kafka. It's counterintuitive, but it's quite fun. You would see how they have simplified their architecture. So Trello did not start with RabbitMQ in the first place. They used to be on Redis. From Redis, they moved to RabbitMQ. And from RabbitMQ, they moved to Kafka. So the first half of this video is kind of like a primer to essential things you need to know about RabbitMQ, and then we'll dig deeper into their architectural change and impact. So as per when they were using RabbitMQ, they had a 15 node cluster of RabbitMQ for everything WebSocket updates. So essentially what happens is whenever, let's say, a card is moved from one column to another column, the people who have subscribed to that board needs to get that update. So the updates are sent to all the relevant users over WebSocket. This is their key use case of it. So essentially, if I talk about like a 30,000 feet view, we'll dig deeper into each one of them. But if I talk about a 30,000 feet view, it looks something like this. That whenever a user performs any action on the Trello UI, API call is obviously made. Once the API call is made, the changes are made in the database. Once those changes are done, it pushes an event to a RabbitMQ cluster. This is the 15 node cluster that I was talking about. It pushes the event to RabbitMQ cluster, and from here, the WebSocket server, they pull the changes. They are constantly pulling the changes from this and then emitting it to the connected users who have subscribed to that board. And this is a high level thing, and we'll stitch together the entire architecture to understand what exactly each component does and how it performs the operation that it does. So end user are connected over WebSocket to get real-time updates on WebSocket servers. And WebSocket servers are consistently pulling the messages from RabbitMQ cluster. Updates from their main API server, as soon as the updates are made, the updates are pushed to RabbitMQ cluster, then pulled and then sent in real time to the user. Now, given that this requires an understanding of RabbitMQ, let's dig deeper into the core concepts of RabbitMQ that are relevant to this thing. I would highly recommend to dig deeper if you are interested, but we'll cover the core key concepts of RabbitMQ that are essential for us to understand this particular dissection. Okay, concept number one, RabbitMQ has something called as a queue, which are essentially message buffers which can hold the message until they are consumed by consumers. Classic queue. But more importantly, RabbitMQ has a notion of an exchange. So when you publish a message to RabbitMQ, you don't publish a message to a queue. You publish a message to an exchange, and exchange routes that message to a queue. So essentially, when you're spinning up your RabbitMQ, you don't have to spin up multiple nodes, like one for exchange and one for your actual queue. It's more about that in that thing, when you spin up a RabbitMQ, it spins up an exchange, or it creates an exchange as per the command that you pass in, and it has some rules configured called bindings, and depending on that, a message is always published to an exchange. An exchange then fans it out depending on multiple things. It has 4 ways to send the message to a queue, which is direct, which is 1:1 mapping, where you say, hey, I want to directly send message to this particular queue, that is direct. Then there is a pattern based thing. Then there is fan out, which is essentially fanning out to everybody. And then there is a message header based routing. Right? So the message is first sent by the publisher. The message is first sent to an exchange. Exchange, depending on the routing thing and depending on the bindings that are created from this to queue, the message are sent to the appropriate queue. Right? That's how RabbitMQ works. Okay. Now you would have seen me use the word bindings. Now what are these bindings? Bindings is essentially the routing rules that tells how messages are routed from exchange to queues. Right? And one queue can have multiple bindings. All of this will come in handy. I'm just laying the groundwork over here. Now, what does a high level flow look like? A message is published to an exchange with a routing key. Imagine a Trello board ID to be the routing key. And then transient queues bind exchange with the routing key. So you create a transient queue, right? And this queue is kind of listening to this routing key. Any message sent for this routing key is immediately sent to this particular queue. Right? Now, here you would see me use a word transient queue. So transient queue is a concept in RabbitMQ where if a queue is transient, which means as soon as the connection is broken, the TCP connection from the machine that has created a transient queue with the RabbitMQ, if that connection is broken, the transient queue is deleted and all the bindings are deleted. Right? This is an example. This is what transient queue is all about. Now, big dots are formed. Now we'll dig much deeper into understand what Trello did when they were using RabbitMQ. So, as we know, the end user is connecting through the WebSocket server to RabbitMQ. So, when the WebSocket server starts, what it is doing? First step, it is connecting to a RabbitMQ, usual connection string. After connecting, it is creating a transient queue for itself. So from WebSocket server to RabbitMQ, one transient queue is connected or is created. Right? Okay. Third, when a user connects to the WebSocket server, so user came online, saw board, subscribed to it. Now this WebSocket connection, now this subscribe is sent. Now when user connects to WebSocket server, user fires subscribe command. Subscribe command is for an entity, let's say a board, a members update, an organization, whatever the user is interested in listening in real time. User fired a subscribe command like board :123 or :1729, whatever. Right? So user fires a subscribe command. Then what happens? WebSocket server. So what happened here? User said, I want to subscribe to board 123. Now WebSocket server will create. So the transient queue is already created. WebSocket server is essentially creating a binding on RabbitMQ over that queue. And that binding says, hey, I am interested in topic T1. T1 is, imagine it's a board ID. Okay. So now what would happen is, imagine whenever there is an update that is coming. So let's say some update has happened. Now this update needs to be sent to the corresponding user. So update is first sent to RabbitMQ exchange. Imagine this is your entire RabbitMQ instance. So update is sent to RabbitMQ exchange. RabbitMQ exchange, given that the message is for T1, right? Given that message is for T1, the queues that have created bindings with exchange on topic T1 receives the message, right? And queue keeps it with itself. Now, once the message is received here, WebSocket servers are constantly pulling from this queue. And once a WebSocket server receives it, it would see which all of the connected users are interested in T1. And WebSocket server sends them that corresponding message. This is your end-to-end flow on how RabbitMQ is used to drive WebSocket-based communication to large number of clients and how this fan-out works. Okay, now let's dig further deeper to see what exactly is their architecture and how they have scaled horizontally, more importantly. So what RabbitMQ did is they have two types of RabbitMQ queues or clusters. First is an inbound cluster, second is an outbound cluster. Now, inbound cluster is one RabbitMQ cluster with 3 nodes in it, right? And it has one exchange. So one exchange is essentially like consider it like your global updates that you are receiving. Whenever something happens, the message is sent to this very exchange, right? This is the inbound RabbitMQ cluster. Then you have 4 outbound RabbitMQ clusters. 4 outbound. And each of the cluster contains 3 RabbitMQ nodes. So that's why 3 nodes here, 3 nodes here, 3 nodes here, 3 nodes here. Now, in total, RabbitMQ has 16 outbound queues here. 16 outbound queues which are distributed across 4 RabbitMQ clusters, each cluster having 3 nodes. Right? That is how the queue is. That is how the queues are distributed in a RabbitMQ cluster. So this is how you get a total of 15 RabbitMQ nodes. Remember when we were starting, we said that it's a 15 node cluster. Let's see. Here it is 15 node cluster. 3 plus 3 plus 3 plus 3, 12 plus 3, 15. This is the 15 node RabbitMQ cluster that we were talking about. Now, this queue, the queues that are created from RabbitMQ cluster, this outbound cluster to this inbound cluster, this are total 16 queues. Consider it as Q1, Q2, Q3, Q4 till Q16. Right. Now, these are not transit. These are like proper queues that are created between RabbitMQ inbound cluster and RabbitMQ outbound cluster. These are regular queues that are created. Now, what is happening is the whole flow is, then everything will stitch together. The whole flow is very simple. The message, the updates, API server did its thing, and then it pushed the message to be sent to RabbitMQ exchange. So it's sent to the inbound cluster. Now what inbound cluster does is inbound cluster knows to which shard does this belong to. But here, Arpit, you never talked about shard here. What is this shard all about? Hear me out. So when a message is formed by the Trello server, right? That let's say in Trello board T1, something happened and this update needs to be sent. So it takes T1, pass through some hash function mod 16. So it gets value from 0 to 15. Right? So this is a client based sharding. Client as in this is where the sharding happens. Right? So it says that this message is for T1 which belongs to shard, let's say 7. So shard 7 is kind of Q7. So this message is sent over here. This RabbitMQ inbound cluster accepts the message. It contains an exchange, it contains a shard key, and then what it does is the role of RabbitMQ inbound cluster is to quickly accept the message and quickly fan them out if required, or send them out or relay them to the appropriate shard or appropriate queue. Right? So message from here received here. From here it went to here. Right? So let's say message was for Q7. Now this Q7 message came to this server. Now here, after it received the message, what it is doing is these servers, WebSocket servers, are the one that have created transient queues here. Okay. And obviously multiple bindings on those queues. So after this node receives the message, it forwards the message to the corresponding WebSocket server. Now here it is possible that this WebSocket server is listing on multiple such queues and all. I just drew it for simplicity, 1:1 mapping, but it's not 1:1 mapping. So any node, any WebSocket server can subscribe to any queue depending on that. So consider this as a mesh topology, right? And this then forwards the message here, and this then forwards the message here, or rather this pulls the message from here and then sends it to the user. This is your flow. But here, if you observe, this is one RabbitMQ cluster. This is another RabbitMQ cluster. So how does this RabbitMQ node send a message to another RabbitMQ node? It's not an inbuilt feature. So here you have a plugin called Shovel. This plugin actually connects the source cluster and a destination cluster. So it consumes the message, identifies the routing, and republishes the message to the second RabbitMQ cluster. So it's very common practice for you to connect one RabbitMQ cluster to another set of RabbitMQ clusters with some routing. So this is where here you get the message, here only it consumes the message, knows where to route and route it to corresponding node, corresponding RabbitMQ cluster. One of the queue receives it. Again, here also there is an exchange, here also there is an exchange. It receives the message and then WebSocket server consumes from it and sends it to the connected user. So this is how the exact flow looks like. Now, here if you observe, this is where your infrastructure scales horizontally. Where if you need more, you can add more instances. Here, the need for horizontal scalability actually came from is because the RabbitMQ clusters are not kind of stable, so having fault tolerance always help. And your inbound cluster, this is a single point of failure. Now, we'll try to address these concerns in a subsequent design, which is where you see Trello moving from your RabbitMQ based implementation to Kafka based implementation. Let's dig deeper. So to understand this, let's start with problems with RabbitMQ. First, handling of partitions is a pain. Experience wise, they were not happy. Second, cluster availability was a problem, typically because of split brain problem. So what happens is, in case of split brain problem, two nodes think they are masters and they act like them, which leads to problems, which leads to conflicts, which leads to a lot of issues. Now, the only way to recover from split brain is to reset everything. Now, as soon as your entire cluster is reset, all the clients, these clients are forced to reconnect. These nodes are forced to reconnect and all. Problem. So, which is where in case of a split brain problem, because your only response is a reboot, it's super expensive. And third, creating transient queues and deleting them is slow and expensive. So it happens on every reconnect. That is also a concern. So this is where the Trello team within Atlassian decided to move to Kafka. Now, what did they do? They went for Kafka because they wanted failovers, in-order message delivery, low latency, high availability, all these things Kafka offers. So what is their architecture? But before digging into their architecture, let's understand their impact. The impact was humongous. After moving Trello from RabbitMQ to Kafka, they utilized 33% less memory. They had twice the CPU utilization. They reduced the cost by 5x. They had one outage with Kafka and 4 earlier, which means with RabbitMQ. So a massive gain on all fronts. Now, what is the flow? What is the new architecture? This is a classic dilemma of push versus pull. Here in previous example, we kept seeing push. And because we're pushing, at last it was pulling. Here it is pull. So the flow is very simple. You still have a queue, but instead of RabbitMQ, all the events from Trello server are essentially pushed to a Kafka topic. Now this Kafka topic, all the updates are then pulled by your socket master. This socket master is a simple process that reads from Kafka and sends it to corresponding WebSocket server. Simple. So these are your WebSocket servers. Now, socket master read the events, filtered them out, found the right socket client to forward to, and it sent message to the socket client through a TCP call, HTTP call. They have not mentioned it in the blog, but through TCP call or HTTP call, the socket master talks to socket client and sends the message, relays the message to that. And this does the same thing that it was doing. It says that this message is for this user or this topic, and this user is subscribed to this topic, and then forwards to those corresponding users. Right? And here we can see how socket master can forward a request to multiple nodes if required, and that node can forward to multiple masters if required. And this is how with Kafka the data is sent, message is sent, filtered and processed and right things figured out, sent here, and it's sent here. So here the life becomes very easy. The architecture becomes very simple. With Trello, it was not the case. you had 15 node cluster and this and that and tuning and blah blah blah. Here your life is very easy. Kafka gives you a lot of guarantees out of the box that makes your life super simple, which is where Trello moved from RabbitMQ to Kafka. And if you observe, look at their architecture is super simple, really horizontally scalable. So if you want to handle more concurrent users in real time, or more concurrent users over real time communication, you keep adding new nodes, and these nodes will keep receiving updates from socket master over TCP connection, and this socket master will keep pulling data from Kafka. Dead simple architecture. And this is what Trello did while moving from RabbitMQ to Kafka. And few key takeaways to wrap this up. First is infra cost can escalate very quickly at scale. So your day zero solution might work fine, but whenever you are scaling, make sure you keep an eye on your infra cost, because a day zero solution might be easy to ship or quicker to ship, but at scale it might bloat up your entire cost. So keep an eye on it. And second, whenever possible, if you can batch, sure batch, because batching is one of the best ways to maximize, or rather to minimize, a lot of API calls. So in one batch you'd get a lot of stuff, right? And yeah, this is all what I wanted to cover today, right? So all the important link, this is taken from Atlassian's engineering blog. I'll link that blog in the iCard below, or below the description you will find that link. I would highly recommend you check that out. RabbitMQ is a fascinating tool and tech on its own. So if you find time, explore it. Whatever we discussed, try to prototype. System design is not about drawing boxes. System design is about at least prototyping, thinking about it from a highly practical perspective, and then digging deeper into knowing what trade-offs they took and why it made sense for their business. So I would highly recommend you to do that. Apart from this, I run courses on system design, and they are highly practical, completely no fluff. And more importantly, I help people build the intuition to build any and every system rather than looking at it from question and answer perspective. The course is filled with brainstorming. We are a small bunch of people in each cohort, and we brainstorm systems, and I try to rewire the brains and to seeing patterns in system design, into understanding, rather more importantly, copy pasting from one system to another system and drawing those analogies. Makes your life super simple. So link for those are also in the description down below. I would highly recommend you to check that out. So yeah, this is all what I wanted to cover. I hope you found it interesting. Hope you found it amusing. That's it for this one. I'll see you in the next one. Thanks, Satan.